in Canada, but he got his PhD in 2016 from the University de Montreal. And he did a postdoc at Los Alamos National Lab. Interesting, Simon. One of your supervisors there was Didier Salmon.
Yeah, correct.
Yeah, and I would brush with greatness in that Didier is good friends with Stéphane Courteau, as in good Canadian friends, as in they were on the same hockey team and all that sort of thing. So, and I went to grad school with Stéphane, so there's a slight connection there.
Nice.
Yeah, so postdoc there, and then he's currently on a named postdoc, the Banting and Sita National Fellow, and he took that to University of Victoria. He's been there since 2021, and he's got quite a few awards for such a young researcher. He had like 5 or 6, as far as I can tell, best PhD in the world awards, one of which was from International Astronomical Union, and also the Los Alamos Distinguished Performance Award for postdocs, and also the Louis Burlingame Award, which is a Canadian honor for research excellence. So thank you so much for being here. The topic is absolutely fascinating. So let's thank Dr. Blouin for being here, and welcome to virtually.
Thank you so much for this kind introduction. Yeah, so my talk today is about white dwarfs. So white dwarfs have been really the center of what I've been studying for the last 8 or 9 years. And more specifically, we'll get to it, but we'll talk about a peculiar population of white dwarfs that are really going against everything we thought we knew about white dwarfs. So those are white dwarfs that seem to stop evolving for billions and billions of years. So feel free, if there are questions as I speak, I don't mind being interrupted. If there are things we should clarify as we go, so no need to wait until the end. So we'll start with just the beginning, just to make sure we're all on the same page. So white dwarfs represent the final stage in the evolution of something like 97% of stars in our galaxy, and about 6% of stars in our galaxy have already reached that stage. So the other ones they're going to get there, but they're not there yet. And that includes, for example, our own sun. So our sun is currently burning hydrogen in its core. At some point, it will run out of hydrogen. It will burn hydrogen in the shell and then burn helium. And this will be during the red giant phase. Eventually, it will run out of all this hydrogen and helium, and it will lose much of its mass towards the end of its life, probably form a nice planetary nebula. And at the center of that, you'll have this little naked core of carbon and oxygen, which is what you get when you burn helium. And that naked core is what we call a white dwarf. So white dwarf is a compact object. So we're talking about something on average that is 0.6 times the mass of the sun, but compressed into a volume that is comparable to that of the Earth. So of course, that means very high density. So the core of a white dwarf, which is the part that's made of carbon and oxygen, has a density typically of the order of 1,000,000 grams per cubic centimeter. So 1 ton per cubic centimeter. So that central core represents 99% of the mass, and then you have some outer layers, so a thin helium envelope, which is like 1% of the mass, and then a tiny bit of hydrogen. So we won't really be talking about those today, but even though they're a very small portion of the white dwarf, you have to keep in mind that they're still very important from an astronomical point of view, because the only thing you can see when you take observations or spectra from a white dwarf is this tiny layer at the top. But we will really be focusing here on this carbon oxygen core, which is really where most of the mass is and where most of the energy is. Okay, so now we'll just look at a small animation that will kind of illustrate how a white dwarf evolves. So I will just start it and stop it so I can describe what this is about. So as this video will go on, we will be just evolving through the evolution of the star. So starting when the white dwarf was just formed and ending when it's very old. So on the left panel, you have kind of a representation of how big the white dwarf is. And the color here is also representative of its temperature. And on the right panel here, you have a Hertzsprung-Russell diagrams that stellar astronomers always like to show. So what you see on this diagram is, so the x-axis is representing the temperature of stars. So you have the very hot stars on the left and the cool stars on the right. And the y-axis is representing the brightness, so bright at the top and cool, dim at the bottom. So the sun is somewhere around here on the main sequence, but here we'll be focusing on this part in the lower left here, which is where the white dwarfs lie. So because a white dwarf is formed after you've gone through all those nuclear burning phases, well, it means that the only thing it can do for the rest of time is to cool down. It has all this heat accumulated in its core, and it's slowly radiating this heat away. So this is what we can see here. So you can see, I'm just going to pause it here. The white dwarf at the beginning of its life was here, and then it just cooled down, so it became dimmer and cooler, and now it's getting on this so-called white dwarf cooling track where we see all those other white dwarfs are. And you can see here that as the time goes by, this color is becoming redder and redder just because it's the black body temperature that's getting cooler and cooler. So notice here that the timescales that we're talking about are of the order of 8 or more billion years. So here, this temperature, 4,000 Kelvin, that's around the coolest white dwarfs we're able to observe today. So the old white dwarfs that we observe, are close to 10 billion years old. So this cooling process is very predictable. It basically just depends on how much thermal energy you have in the white dwarf in the first place, and then how fast this energy is leaking into space. And those are things that we can model, provided that we know the composition of the star and the physics of the white dwarf, so the conductivity and the radiative opacities and all those things. But those are things we think we know pretty well. And so this then opens up the possibility of using white dwarfs as cosmic clock. So the idea is that if you're able to measure the surface temperature of a white dwarf, well, you're also able to tell how old it is because we're able to model this cooling process. So in the details, you also need to know the white dwarf's mass and its composition, but those are also informations that we can gather from spectroscopic or photometric observations. So you get as much information as you can about the white dwarf, and then you model its cooling, and from that you can infer how old that white dwarf is. So this is something that people have been doing since the 1980s, basically, and the models are constantly refined, and we're getting better and better constraints on the ages of different stellar populations within our Milky Way, so like the galactic disk, the galactic halo, globular clusters where you have older white dwarfs. And so this is really a powerful tool because in general, measuring the ages of stars is a very difficult problem, simply because the observational properties of stars tend to not change much as they evolve. So even if we take the example of our sun, for which we have really, really good observations, the only reason why we can pin down precisely the age of the sun is that we have meteorites that we can study in the lab here on Earth, and we know those meteorites come from material that was formed at the same time as the sun. But just by looking at the sun, it's very hard to tell its age. So white dwarfs are really an exception in this respect because of this continuous cooling process. Okay, so now as the white dwarf cools down, there's something really cool that happens at some point, and this is called the core crystallization of white dwarfs. So you have to imagine that in the core, you have this very dense plasma. So you have carbon and oxygen, but this carbon and oxygen is fully ionized. So you have a sea of electrons, and then you have those bare carbon and oxygen ions. Those ions, they have a positive charge, so they interact very strongly together through Coulomb interactions. And I say very strongly because the density is very high, which means they are packed very closely together. And so, you know, the Coulomb interaction goes as 1 over r squared. So if you have a high density, you have very strong Coulomb forces. Now, initially, those Coulomb forces don't matter too much because the white dwarf is extremely hot. And so your carbon and oxygen ions are moving very fast, and they don't feel these interactions too much. But as the white dwarf cools down, the ratio between the Coulomb interaction and the thermal energy of the ions increases. And at some point, this interaction becomes so strong that it just freeze in place into a body-centered cubic lattice structure. And so they are squeezed from every direction, so they just stay in place. And so this is really a liquid to solid phase transition. And it is a first order phase transition, which means that just as when you freeze water, there is a release of energy when you go from the liquid to the solid phase. So in the form of a latent heat. So this latent heat is like a new source of energy for the white dwarf. So remember, it's just cooling down from its residual thermal energy. But then when it freezes, you have this little new source of energy that you need to get rid of in order to continue cooling down. So this creates a small slowdown in its cooling. So something like 0.5 billion year pause in the cooling. And that's well known, and that's been modeled for a few decades. Now, there's something else that happens when you freeze this carbon-oxygen plasma, and it's something that happens basically whenever you freeze a mixture of different species. So one example I like to give is the example of seawater. So if you freeze seawater, what will happen is that the ice, the salt in the water will tend to not be included in the ice. So the salt gets pushed into little brine droplets, and you have a salt-free ice. So really, there is a separation of the mixture during the cooling process. Let me just back up quickly to make sure I'm not sure exactly when we lose the room. So we have this freezing process, it releases latent heat, but there's something going on top of that, which is that in general, when you freeze a mixture of two species, there is a chemical separation process that goes on where the solid that you form doesn't have the same composition as the liquid that's coexisting with that solid phase. So a classic example of that is when you freeze seawater. So the salt tends to not get incorporated into the ice, and it gets expelled into little brine droplets. So you have really a separation of salt and water during the freezing process. Another example with some practical implication is freeze distillation. So if you were a settler in colonial America, that's how you would make hard liquor. You would take some apple cider, which is not that high in alcohol, and you would let it freeze in a bucket outside in the winter. And then you come back a couple hours later and you remove the ice and just keep the liquid because the alcohol gets concentrated in the liquid, and you mostly have only water in the solid. So it's a very general thing that when you freeze a mixture of two species, you have this separation. So of course, it also happens in our white dwarfs, except in our white dwarfs, we're separating carbon from oxygen. So
quick question, which is, how come you're calling it liquid and not plasma?
Well, so it's a liquid plasma.
Okay.
Or I mean, so the transition, so it is a plasma. It is not a solid because there is no nice ordering of your ions. So you can call it a strongly interacting gas or a liquid or a fluid. It's somewhere in that continuum. But for sure, it becomes a solid plasma when it freezes, because it is still a plasma because the electrons are fully ionized, but it is organized in this nice atomic structure, so it is a solid. So when you freeze that carbon-oxygen plasma, what happens is that the crystals that you form, they tend to be enriched in oxygen. And so you first start crystallization at the very center of the star. And the reason why you first freeze there is simply because that's where the pressure is highest. So it's more conducive to making a solid. And so you make a solid there. And that solid will be enriched in oxygen, which means that the layers on top of that in the star will lose some oxygen to form that crystal. And as the star freezes, you add more and more solid layers, and each of those layers has more oxygen. So gradually, you're building a concentration gradient where you have more and more oxygen at the center of the star compared to the surface. And you were starting from a point where it's pretty much homogeneous in the core. And so on net, what you've done is that you've taken more heavy ions, so oxygen 16, and you've pushed them at the center of the star, and you took the lighter stuff, carbon 12, and you pushed it to the surface of the star. And so that means you have released gravitational energy. And this release of gravitational energy is, again, another source of energy that's slowing down the cooling of the star while it is crystallizing, because you need to get rid of this excess energy. And that's another 0.5 billion year or so of cooling delay for the star as it undergoes this crystallization. Okay, so with this background in mind, now we'll look at some observations that really motivate what I'm talking about today. So in 2018, we had this release of data from the Gaia Space Observatory from the European Space Agency. So Gaia is a space observatory that's measuring very precisely the positions of billions of stars in our galaxy. And that includes hundreds of thousands of white dwarfs. And that's been a really big game changer in our field, because when you measure very precisely the position of stars at different epochs, you can then know the distances of these stars from the Earth. And if you know the distance to stars, you resolve this big degeneracy between, is it a bright star that's far away or a dimmer star that's close to us? And so before Gaia, we knew precisely the distance of just a few hundred white dwarfs, but now it's like 350,000 white dwarfs. And so this allows us to do things that were simply impossible to do before, because if you know the distance to a white dwarf, then you can also infer its radius, and from the radius you can also infer the mass, because white dwarfs obey this very well-defined mass-radius relation. So there's just a lot that you can learn. Okay, so this is how white dwarfs look in the Gaia data. So this is, again, my Hertzsprung-Russell diagram. So I've labeled things here so everything is clear. So, I mean, on the top here, you have hot and bright stuff, and here you have the cool and faint stars. So my white dwarfs, they evolve from the top left to the bottom right. What was unexpected is that there's lots of structure in this diagram. So we were expecting like basically just one big cooling track with some scatter around it. But there are three clear features that emerge here. So first, there's a bifurcation here. So you have a separation here between those two branches. They've been called A and B. So we won't really be talking about this, but this is purely an atmospheric effect. So some white dwarfs have a different atmospheric composition, and this creates this separation. But what we'll really be talking about is this Q branch here. So this Q branch is very peculiar. It was called Q for question in the original Gaia paper, because it is basically perpendicular to the evolutionary tracks of white dwarfs. So the white dwarfs, they start from here and they go down there. But this feature here is just transverse to it. So we know it's not an evolutionary track. It is something else. For some reason, the white dwarfs, they kind of pile up at those specific temperatures and luminosities. And so there was this very nice Nature paper the next year that showed that actually this Q branch is exactly where current models predict that white dwarfs should crystallize. So what you have here in blue are cooling tracks for white dwarfs, so they just cool down along those tracks. And in orange, what you have is the region that brackets where the white dwarf is in the process of crystallizing. So if we take a white dwarf that follows this track, it would be completely, its core would be completely liquid or fluid until we reach the first orange line. And then it would start freezing, and it takes a while to completely freeze the star. And then when you reach the second orange line, then it's completely frozen and it continues cooling down with a frozen core. So the basic idea in that paper was that when you have this freezing process, as we've seen, we have this release of latent heat, and we have this release of energy from the separation of oxygen and carbon. And the result of that is that you have a slowdown in cooling in the same way that you have a slowdown in cooling when you put a glass of water in the freezer. And therefore, it's not surprising to see many more white dwarfs in this region. It's simply basically a traffic jam of white dwarfs. They're evolving more slowly, and therefore, we should expect to see more in that region. So that was all really cool results, because it was basically the first observational confirmation that white dwarfs actually freeze. But it turns out that it doesn't work when you look at the details. So you can look at this more quantitatively and count basically how many white dwarfs you have here compared to before or after. And then you can infer from that how long the cooling delay due to crystallization must be. I'll just skip this. And the conclusion from this more detailed analysis is that actually some white dwarfs must stop evolving. They must stop cooling for at least 8 billion years. So this is purely derived from the observation. So if you don't have that, you cannot have this overdensity that we see on the Q range. It is not as sharp as we see it in the observations. So this is 8 billion years beyond the cooling delay that we expected from the release of latent heat and the separation of carbon and oxygen. So there's really something else happening on top of that. And then, of course, the question is, well, what is it? What's happening? And it's really important that we figure it out, because if there's a phenomenon going on in all those stars, we want to know what it is. But B, because if we want to use white dwarf as precise cosmic clocks, well, we want to be able to convince people that our models are actually able to accurately model this cooling process. But if we're missing a multi-giga-year effect, well, obviously it doesn't look very good. So far I've talked about the core as being made of carbon and oxygen, but there's a third species that's there in a trace amount, so a few percent, and that's neon-22. Neon-22 is there basically just because when you do hydrogen burning in the previous evolutionary phases, the slowest step in the CNO cycle involves nitrogen-14, and this nitrogen-14 then captures some alpha particles to end up being a neon-22. So this is well known from stellar evolution that you have this trace of neon-22 in white dwarfs. Now, it's a small trace, but it's an interesting trace because contrary to the carbon-12 and oxygen-16, it has 2 extra neutrons in the sense that you have 10 protons and 12 neutrons, whereas oxygen-16 has 8 protons, 8 neutrons, and carbon-12 has 6 neutrons, 6 protons. And those extra neutrons are really consequential in the context of. So to understand why that's the case, we can start with we can make a simple thought experiment. So let's say we have a white dwarf that's 98% carbon oxygen and 2% neon, and everything is spread evenly in the star, which is actually very close to what details models will predict. Now, assume there is a process, just let's assume it, that takes all the neon that's in the star and concentrates it at the center of the star. Now, when you do this switch, there is one quantity that must remain constant at the center of the star, and that's the electronic density. So the reason it must stay constant is that a white dwarf is supported by the degeneracy pressure from the electrons. So the whole structure of the star is determined by the electrons, not by the ions. And so if the whole mass of the star doesn't change, the pressure at the center must stay constant if you still want to support all this mass. And so the electronic density must also stay constant. But if the electronic density stays constant, here it means that the mass density must increase because neon 22 is, you have to carry those extra neutrons with it to provide a given number of electrons. So you have 22 units of mass per 10 electrons. And so that's a different ratio than if you have just oxygen or carbon. If you increase the mass density at the center of the star, then, I mean, what you've done is you've put mass at the center of the star. And so you've put mass at the center, down the gravitational potential energy well. And so you've released gravitational energy. And so it's a simple back of the envelope calculation that one can make of like how much energy is this actually releasing. And when you do that calculation, you find that the amount of energy that this is releasing is enough to stop the cooling for 10 billion years. So it seems like if you have a process that can do that, then we can explain those puzzling observations. But now, how can you actually bring this neon to the center of the star? So the process that's been studied for a while now is simple gravitational settling. So the idea is that the neon 22 is heavier. So even though it's a dense plasma, things can still move. And so the neon can kind of slowly make its way diffuse towards the center of the star. So this is what this little animation is showing. So this axis here is just showing here you have the center of the star on the left and the surface on the right. And here is how much neon you have. So you start with 2% everywhere. And gradually, the neon is shifting towards the center of the star. But as you can see, this is not very efficient. So at the end of this calculation, we have, we're at like 2.2% neon at the center, maybe, not more than that. So that really doesn't release a lot of energy. And the fundamental reason why it doesn't release a lot of energy is that once you freeze the star, you cannot move things anymore because the diffusion coefficients become too small. So the same way it's easier to, diffuse a dye in liquid water. If you try to diffuse a dye in a block of ice, I mean, it won't diffuse much. It will just stay at the surface. So it's really the same idea here. So we need another way of transporting all this neon to the center of the star. And the way we found of doing that is, again, going back to this idea of chemical separation during the freezing process. So the calculations that had been done before were always focusing on a two-component mixture, so carbon and oxygen. And here what we've done is that we've performed new calculations that take into account the fact that there is also some neon in there, and we want to know how the neon concentration differs between the liquid and the solid phase. So there are different ways of doing those calculations, but one way is, for example, with molecular dynamics simulations. So you basically put all your ions in a box, and then you put half of the box in the solid phase and half of the box in the liquid phase, and you let things evolve, and you see how those little impurities here in yellow, which could be neon, but for those specific pictures, it's actually not neon, but it's not important. But you can see whether they get incorporated into the solid or excluded from the solid. So in this case here, as we dial down the temperature, the crystal grows. So we see here only half of the box is solid, whereas here there is lots more of solid, but all those impurities get pushed out into this little liquid pocket. So they really don't want to live in this solid. So what we found for our carbon-oxygen neon mixture for white dwarfs is that the neon tends to be expelled from the solid phase. So the more neon we have in the liquid, the more it's expelled from the solid phase. And this is interesting because neon 22 is much heavier than oxygen 16 and carbon 12. So if you remove it from the solid phase, you end up forming buoyant crystals. And so this is really completely rewiring like how we were thinking of crystallization. So the classical picture is that you first freeze at the center and the solid is heavier than the liquid, so it just stays there. And then you add another layer on top of that and another layer on top of that and another layer on top of that. And that's this the picture shown here on the left. But if you have enough neon in the core, what you get is more something like what you have on the right. So you form those little crystals, but those crystals, because they're poor in neon, they're less dense than the liquid around them. And so they start floating up just like, ice cubes in water. And by floating up, they're displacing liquid down, because if you remove the little crystal, you're leaving a hole behind, so the liquid has to fill that up. And that liquid will, by definition, be more rich in neon because you've pushed neon out of the crystal when you formed it. Those crystals, they will eventually melt when they rise up. And so you have this kind of convective-like motion where you have floating crystals pouring neon and sinking liquid rich in neon. And gradually, as you do that, you're increasing more and more how much neon you have at the center of the star. And our calculations predict that this will go on until you have about 20% neon at the center of the star. So it's not 100%, but it's much more than 2%. And so it releases a really large amount of gravitational energy. So basically, the end state will look like this. And with the neon-rich nugget at the center, and then the neon-free core outside that. And a key prediction from those calculations is that whether you have or not this process, which has been called distillation, will depend on the exact composition of the star. So the prediction is that you need a larger amount of neon-22 than what you expect in the average star. And that would explain why only some white dwarfs show this extra delay of 10 billion years. So for example, our sun, we expect it will have only 1.4% neon or so when it becomes a white dwarf. So it should not have this process. But there is a significant fraction of white dwarfs that will have it, and that gives you this neon rich core. So what we did is we took this picture that we developed and we put it into actual evolutionary models of white dwarfs. So what you see on the left plot here is, as a function of time, how the composition at the center of the star evolves. So initially, it's basically 50-50 carbon, oxygen, and then some small trace of neon. And then when we reach this little circle here, that's when you start freezing. And so you have this distillation process that is gradually increasing the neon concentration in the core. And note that this process here takes of the order of 10 billion years. So it's a very slow process because as you are pushing neon down, you're releasing gravitational energy and you're slowing the cooling down. And so there is kind of a limit to how fast this process can go. If it goes too fast, then you stop you stop forming crystals, and so the process stops, and then you start cooling down again, and it starts again. And so there is this feedback loop where it's just halting the cooling for billions of years. And that's what the panel on the right is showing here. So what you have is the surface luminosity of the star as a function of time. So the dashed line are just standard models, and the solid lines are the models where we add the cooling delay on top of that. And so you can see that those stars, they stay basically at the same luminosity for 10 billion years. And what's quite funny is that this luminosity actually is quite high. So it's comparable to that of some main sequence stars, so M dwarfs. And so those stars, they stay as bright as some main sequence stars for 10 billion years. And so really, what this is showing is that not all white dwarfs should be considered as dead stars. There are ways to keep white dwarfs shining as bright as what we consider to be actual stars for billions and billions of years. So when we simulate the evolution of the white dwarfs in our galaxy using those models, we are able to replicate this overdensity in the Q branch. So this is what the plot on the right is showing. So this quantity here is, so this is basically just a histogram counting how many white dwarfs we have as we follow this cooling sequence. So in black, you have the observations, and the big peak here is simply, the Q branch, this overdensity that was discovered with Gaia. In blue, you have the histogram that we get with standard cooling models, and in red is what we get when we include, when we allow for some white dwarfs to undergo this additional cooling delay from this neon separation process. So it seems to work very well and to explain the observational properties of this Q branch. So those Q branch objects, they are pretty massive white dwarfs. So, around 1.1 solar mass, which is about twice the mass of a normal white dwarf. And so we think that the reason they are acting like this is probably because they have a merger origin. So there are different ways to get there, but it could be just two white dwarfs merging together forming a bigger white dwarf. And during this merging process, you can have thermonuclear reactions that increase how much of those neon 22 impurities you have in the star. And so that's probably what's going on here with those stars and why they're acting differently. Because if you don't have enough neon 22, then you don't get this process. And as I said, for example, for when our sun becomes a white dwarf, it shouldn't have this process. Now, there are other population of stars in our galaxy that should also have lots of neon 22 without being more massive. And we can find those in some globular clusters. So NGC 6791, is an open cluster that is metal rich. So it has something like 3% neon in its white dwarfs. And if we go back here, we see that at 3%, we should expect distillation to take place in those stars. And it seems that indeed it does. So what you have here is just binning how many white dwarfs there are as a function of their brightness. And so the first peak here, nobody knows exactly what it is, so I won't talk about it. But the second peak here is just because of the age of the cluster. So you don't have white dwarf cooler than that, simply because the cluster is not old enough. So if we try to, if we simulate the cooling of white dwarfs in this cluster using standard models, this peak here happens at too cold temperatures. So it's simply, it's too late compared to what we see in the observations, which shows that those white dwarfs are delayed in their cooling. And indeed, when we include this distillation process, now we can fit the location of this peak. So this is a nice independent confirmation that this process is happening in different types of stars for different reasons. So some are merger products and some are just white dwarfs that happen to have a high neon concentration in the first place. So this really yields some additional credibility to this whole scenario. So yeah, on this, I'll just give you my quick take-home points. So I think white dwarfs are objects that if you open any textbook, you will learn that they simply cool down for the rest of time. And this is right, but it's a bit incomplete because we now know that there is a significant population of white dwarfs that simply stop cooling for billions and billions of years and actually shine as bright as some main sequence stars. And we now know that this extra energy that's allowing them to shine so bright for so long is this liquid solid distillation process whereby you separate the chemical species in the star and you release gravitational energy. So thank you so much for your attention, and I look forward to your questions.
We might have to go for the next thesis defense, but questions are welcome. Any questions? Yeah.
Thank you for the talk. That was really interesting. But what's the reason why nitrogen or why neon would be the third most abundant element that is expected? Why not something like fluorine or some other heavy element?
Yeah, so this is really so when you do your CNO cycles, there are many steps, and there are some steps that are faster than others. And so the steps that are faster, they don't leave any isotopes afterwards, because as soon as you complete the previous step, you also do this one. But there is one step that includes nitrogen-14, and that one is just slowest. And so that's why you end up with lots of nitrogen-14 when you end hydrogen burning. But then you have helium burning. And during helium burning, this nitrogen-14 is easily, will easily capture those helium nuclei to go all the way to neon-22. So you could have some fluoride, I guess, with just one alpha capture, but I think the amount is really, really small. Then in some white dwarfs, so for those merger models, so this idea that those white dwarfs come from mergers, there was actually a prediction that there's lots of magnesium-26, but it turns out the magnesium-26 is doing the same thing as neon-22. It's also triggering this distillation process. The key is you need an isotope that has extra neutrons. So there are many different isotopes that can do the same job.
Thank you.
I have a question up here.
Yeah, go ahead.
Oh yeah. Sorry for the lack of video. Really fascinating talk. Is there anything in geophysics that's parallel to this, or is this just utterly negligible? These effects in the formation of cores of planets and mantles of planets?
Yes. So there's no perfect analog, but I mean, this separation of elements is something that's, in geophysics happens all the time. That said, I've not been able to find any example where this actually releases gravitational energy in any amount that would be,
I see. Yeah. Thank you.
It is raining and it's in the middle of Saturn right now.
Yeah.
I have a question. I think just maybe two slides back, there was a nice HR diagram with white dwarfs on it. And I was wondering how you get a mass for that Q branch. How do we know that they are massive?
Yeah, good question. So, so the idea is that you measure two things basically. So first you measure the distance of the star, and second you measure its brightness. And then we have atmosphere models that tell you how bright a star of a given temperature should be if you're at some given distance. And so by comparing how bright it looks to how bright it should be, well, you know the ratio of radius to distance, so the solid angle of the star, but you already know the distance from Gaia, and so that gives you the radius. Then the mass, we don't know it directly, but we infer it from the radius because we know that white dwarfs obey this mass-radius relationship. So that's the idea. It's not directly measured; it's inferred from the radius.
Yeah.
For some systems, you'll be able to measure the mass, of course, in binaries if you have good astrometry. But yeah, it's just exceptions.
Very good. I see no more eager hands. Let's thank our speaker one more time. Thank you so much.
Thank you.
Yeah, very good. Thank you so much for connecting. Even if we didn't get you on an airplane to get you here, but thanks for giving that talk. Very nice talk. Very informative.